Number 16 reads, determine the bond energy of a chlorine-chlorine bond given the following information. Methane reacts with Cl2 to give you this methyl chloride and HCl. Okay, we don't need to know exactly what they are, but here's some reaction, and we need to figure out the bond energy of this ClCl bond here. We're also given these data. This tells us the energy that's stored in these bonds here. An HCl bond, a CCl bond, an HC bond. Okay? If this is the amount of energy stored in an HCl bond, this is also the amount of energy required in order to break that bond. Okay? So, we're given an enthalpy of reaction, a delta H of reaction. This tells me the overall amount of energy that's released, because it's negative. It tells me the overall energy that's released after considering how much energy it took to break these bonds and how much energy it took to make these bonds. Okay, that was pretty important, what I just said. Is that in order to make my products, which is where I'm going to be in the end, I first have to put energy in to this bond and this bond, the CH bond and the ClCl bond. I have to put energy in order to break them. That doesn't seem so bad, conceptually. The weird thing that throws everybody off, even me, is that whenever these bonds are formed, the CCl bond and the HCl bond, whenever they're formed, energy is given off. Okay? Energy out. Whenever a bond is formed, energy is given off. How can you remember this? Just think, if I need to break a bond, think of a bond as a stick. Well, if I need to break this bond, I'm going to judo chop it. So it puts energy into the bond in order to break it. Alright. So let's get cracking. How do we do this? We need to take into account all of the energies that were put into the system and taken out of the system. Here we go. What's the energy in? I put, I need to look for a CH bond to break. So I had to put in 414 kilojoules into this bond in order to break it. So it's a positive because I'm putting energy in. I need to break this ClCl bond. Oh, but wait, that's what I'm looking for. Okay, so I need to give this a name. Since I don't know the value, I don't have a value for ClCl, I need to give it a name. Now, we could call it a number of vulgar names, you know, because maybe we don't like doing chemistry. I like doing chemistry. So I'll call it X, since it's not too scary. So let's just call it X. Okay, it's a positive because I need to put energy into that ClCl bond in order to break it. These two bonds, the CCl and the HCl, need to be formed. That's energy out. So it's going to be a negative and a negative. A CCl bond was formed. That's 339. Negative because energy is given off because the bond was formed. HCl, here it is, 431. Negative energy given off. Bond was formed. What does this whole thing equal? This whole thing equals the amount of energy that was given off after everything was done. The delta H tells you, after everything's said and done, what happens. Well, overall, minus 113 kilojoules was given off. Now, I don't have my units, but everything is given in kilojoules per mole. Okay. I need to solve for x. This is what the question wants. So, all I do a little algebra, add 339, add 431, subtract 414. Add 339, add 431, subtract 414, and your final answer is 243 kilojoules per mole. This is the amount of energy that I have to put into the chlorine-chlorine bond in order to break it. Judo chop!